We all know that adding two arrays means adding corresponding elements and storing the result in a third array. So hello everyone, in today's session we'll be implementing this logic in pure assembly language. Let's see and understand how exactly it's done. So the first thing we notice is nothing but assembler directives. At first we have something called area. Area is an assembler directive which defines a section of memory to store all this particular information. Array add is the name I have given to this particular section of memory. Code here indicates all these are nothing but instructions. Read only because we don't want any modification to be happening to this particular code during runtime. Entry here is an assembler directive which indicates where exactly execution should start. If you write entry here, then the very next label seen after this particular assembler directive is the position where execution starts. Start, loop, stop, A1, B1, C1, all these are just labels, and the purpose of labels is to represent certain memory location. That is, they represent certain memory address. The first thing we see is the LDR sudo instruction. The purpose of this particular instruction is to copy the address associated with the label A1 into register R0. Similarly, the address associated with label B1 is stored in R1 and address associated with label C1 is stored in register R2. The next thing that we do is store a value 5 into register R3, which is currently acting as a counter, which stores the length of our array. Before we go ahead with our logic, let's see what are these labels. Okay. If you notice here, A1 is label associated with this particular array of data 12045, and B1 is the label associated with this particular array of data which is 51336, and you can see something called DCD. What is DCD? DCD is define constant double word. The purpose of writing this particular assembler directive is to ensure that each of this particular element of array is provided with 4 memory locations, because we consider each of this element to be of 32 bits each. And same with the label B1, it is associated with these elements. One more thing that you should know is whenever I store the address associated with label A1 into R0, R0 will act as a pointer and it will start pointing at the very first data which is stored under this particular label. Okay, C1 is the label associated with our result. And what is this here? See, this is again the assembler directive area which defines a section of memory so that our result is stored. Array data is a random name we have given, and data is written here to ensure that this section of memory stores data, not instructions. Read write because we should be able to modify this particular content during runtime, and end indicates the end of source file. Now, since we have already finished understanding the different assembler directives and the labels existing here, let's move to our actual logic and understand what exactly is happening here. The first thing we notice here is LDR R4, content of R0, #4. What does this instruction actually do? Whatever is the location pointed by R0, in our case it will be pointing at the very first element of this particular array. So this particular content should be copied to register R4 and R0 should be incremented so that it points at the next data. Why is it 4 here? Because 1 here is written something like this in memory, and 2 will be written something like this. That is, one element will occupy 4 location. So because R0 is initially pointing here, So that it reaches this particular location, we need to add plus 4. That is what is happening here. Okay, and the reason it is written as 0100 and all this instead of this is because our system, that is LPC 2148, follows Little Indian concept. So because of this reason, you will notice that in the memory, contents are stored in this particular order. That is, in the lower memory address, least significant byte will be stored, and as we move to higher address, the higher bytes will be stored. So this is how it will be stored in the memory, and R0 will be pointing at this particular location initially. So at the end of this particular instruction, R4 will have content 1. At the same time, R0 will be pointing at the next location. Now since we know how exactly this instruction works, we know that at the end of this particular instruction, R4 will be holding the value 1. At the same time, where will be R0 pointing at? It will be pointing at the next element. So what should be the result of this particular instruction? R5 should be holding which value? The very first element. Okay. At the same time, where will be R1 pointing at? It will be pointing at the next element. Okay. So what is happening here? Addition between R4 and R5, and the result is stored in R6. So what's the result of adding R4 and R5? R6 will hold a value 6. So this answer here will be stored using this instruction str in the location pointed by R2. Which location is pointed by R2? If you notice here, R2 is pointing at the label C1. So the result R6, okay, which is 6 in our case, will now be stored at the very first location that you can see under the label C1. It's initially initialized to 0, but now it has the very first element 6 stored in it. Okay, and one more thing we notice is R2 is incremented by 4 because even this value 6 occupies 4 locations. So R2 will be now pointing at very next location so that the result of the next addition can be stored at that particular location. We are subtracting R3 by 1. See, R3 is our counter through which we know there are 5 elements to be added. So now why are we reducing it by 1? Because we have already completed one iteration and there are just 4 more additions to be carried out. Okay, one more thing, if you notice, yes is there. What this will do after subtraction based on the result, now our result is 4, right? Based on that, the CPSR conditional flags will be updated. Once they are updated, next instruction will check if a particular flag of CPSR, which is nothing but Z flag, is set as 1 or not. If it is actually set as 1, this condition will become false and we will move here to stop branch stop, which is an infinite loop. But if R3 minus 1 is not equal to 0, in that particular case, Z flag of CPSR will be updated as 0 only, and until Z is 0, this condition is true and we will branch back here. This is branch if not equal. Not equal means what? We are checking if Z is not equal to 1. In that particular case, we are branching back here. So the next thing that we notice is R0 is pointing at 2. So what value will be received by R4? Same value 2 will be received by R4. So it gets updated here. What happens to R0? Its position is incremented by 4. It will lead to R0 pointing at the next element. At the same time here, R1 is currently pointing at 1. So when that value is loaded to R5, what is our new R5 value? It is nothing but 1. But what happens to R1? It will start pointing at this particular element. And next task that happens is addition. So what is R6? What is new R6 value? R4 is 2. R5 is 1. 2 plus 1 is 3. Okay. Next thing we do is store this value in the location pointed by R2. R2 is pointing at this particular location, so I'll store value 3. Okay, and after that what happens to R2? R2 will start pointing at the next location. So this is the final result we are supposed to obtain for the addition of these two array. Let's see if that happens or not. First of all, let's check if there are any errors. No errors, so we'll go ahead here. Okay, now let's see what exact address is associated with A1. It is 2C. At the address 2C, I can see values 12045 as we can expect from this. Okay, at the same time, the address associated with B1 is 40 51336 as expected. And let me open another memory window. And now what address is associated with C1? It is 0x4 and all zeros. And at the end of this particular code, what should happen? The result of the addition between the elements of A1 and B1 should be stored at the location pointed by C1. That is, here I should see my final result. R3 is loaded with the counter value, which is 5. If the length of array is either extended or reduced, then you will have to change the counter value here. I'm loading the content pointed by R0 into R4. Yes, you can see that happening. And what about R0? R0 address is incremented. As you can see here, from 2C it is changed to 30 because now it will be pointing over this location. Okay. At the same time, because of the next instruction, the first element is loaded to R5 and R1 is incremented so that it can point here. Okay. So next what should happen? Addition. Yes, that has already happened. And the next thing we see is store operation happening. As you can see here, the first element of our final result is stored in the location pointed by C1. Now we'll go ahead. What has happened here? R3 content is subtracted by 1, so instead of 5 now it is 4, and CPSR is updated. As you can see here, Z is 0, because of which this condition is true and the loop happens. Okay, so here next thing we notice is the next content will be copied. Okay, and it is placed in register R4. Similarly, here the next content will be copied and placed into register R5. Their result is stored in R6, and then that result is stored in our destination. And this continues happening. It happens until the addition of all the elements are completed. Okay, now you can see that R3 keeps reducing. Now it is 1 because only the last element addition is pending. Okay, and the result is B, and this will now be stored here. So we have the answer 6337B stored in our final destination. What should happen now? The result of R3 will be 0, because of which this condition will be false, and we are jumping here, which is an infinite loop.